cubes are used to measure quantity of space. Now, space is related to the idea of solids, as you recall. And we're going to talk about a number of solids, but the unit that we're using are cubes. Now, for the rectangular solid, and here's the rectangular solid depicted as we had it before, we make the calculation for volume, or the quantity of space that can fit, the quantity of stuff that can fit within that box, if you will, by multiplying or thinking about area of base times height. And I want to show it to you like this rather than just give you the final formula, because this idea, this concept, applies to a number of different figures. Now, the base is what this appears to rest upon. It's sort of resting upon a rectangle. So it has a rectangular base. The area of the base then is length times width. So the overall formula for calculating volume is length times width times height. And notice that we're just multiplying the three dimensions here. And I want to say it that way because remember when we talked about area, I said that, gee, we can think about area as in terms of the multiplication of a dimension times a dimension in the perpendicular direction. It was length times width, remember. And now we have that idea in three space, or in three-dimensional terms. So it's length times width, and then from the perspective of this width, the height, you see, is perpendicular to the width. Height is also perpendicular to the length. And so all of these are perpendicular to one another because we have a three-dimensional object. All right, that's kind of maybe more than you need to know. But volume then is length times width times height, and if we put some measures on here, let me do that. Let's just put some measurements along these dimensions. What if this is 9, and let's call it inches, 3 inches, and let's say 4 inches. So all we have is 9 times 3 times 4, and multiplying, we find the volume to be 108. Now 108, what is 108 what, you see? Well, we're measuring in cubes, in little tiny cubes, you see, and we're saying that it would take 108 little tiny cubes that are each a cubic inch to fill that box. So 108 cubic inches for the volume of the box, or the rectangular solid. For a cube, it's a variation along the same theme. It's the idea of area of base times height. If we forget the formula, we can use this idea. The base is a square base. So the area of a square, gee, we're just multiplying the sides, so it's side times side for area of the base. The height is also designated S. You see, all of these dimensions are just S, sides. And so it's 3 factors of S, or S cubed is the fast way to think about it. And if the cube is 3 feet on a side, then we would replace S with 3. Now cubing means we have 3 factors of this base. So it means 3 times 3 times 3. 3 times 3 is 9, 9 times 3, 27. So the volume of the cube is 27 cubic feet. Here's the cylinder, and once again, for the volume, we think of it in terms of area of the base times the height. The base of the cylinder is circular. So for this part of the formula for volume, it is the formula for the area of a circle. So it's like the area of a circle times the height for the formula of the volume of the cylinder. And so it's pi r squared h for the overall formula. But this part of it is area of the base. All right, that's I think is an important idea. Well, to use the formula, we use the information that's given up here. Now, notice that the formula for volume involves radius and not diameter. So if we're given diameter, we have to make the calculation for radius in this process. So if we're figuring the volume of this cylinder, given the information that's up here, we would go through and fill in for the letters. We have pi, let me put it as 3.14. Times the radius. Well, let's see, the radius, 6 centimeters all the way across. So it's 6 centimeters all the way across this circular base. That's a diameter then. And if this is 6, then half of that would be 3. So from here to there would be 3 centimeters. So it's 3 that we're using in our formula, and the height is 8. And now we multiply it out. 3 squared is 9. You see, we need to do this first, and then the 9 times the 8 times the pi, and it turns out that the volume is 226.08, and it's cubic centimeters here. It's the cube on whatever the unit is. Here's the most interesting figure of all. It's a sphere. Now this is like a basketball or a baseball or something like that. So it's kind of a three-dimensional circle idea. We can't quite use the notion of area of the base times the height, can we? That would be a little bit inappropriate here. But I will tell you a story about where this formula comes from, and I'm going to make this as fast as possible. It's not something that you may or may not remember the story, but the story may help you to remember the formula for the volume of the sphere. The formula is 4/3 pi r cubed. Now, where in the world can this possibly come from? Well, it turns out that this formula is arguably, maybe not, the greatest achievement for one of the greatest mathematicians who ever lived, and that would be Archimedes. He's my favorite ancient mathematician. And if you have a chance, study the history of Archimedes. He was quite the great man. But here's what he did to come up with this information. A lot of the Greeks, and he was a Greek mathematician, they were involved in experimentation often. They would experiment a lot to see if a formula worked. Rather than derive it algebraically, they would experiment with practical problems, and then they would establish a formula and then reestablish that it worked and it worked and it worked. You know, that's the way that they dealt with problems. Well, with the sphere, Archimedes pondered this for a long time, and here's the way he performed experiments, though, to come up with his formula. He took a cylinder, and he made a cylinder that corresponded with the size of a sphere, so that he could put the sphere inside the cylinder. Let me show you what I'm talking about. Here is a cylinder with a sphere inside it. All right? And to make the calculation of volume, or to think about it, or to experiment with it, he took the sphere out, first of all. Then he would fill the cylinder with water. And then he would slowly drop the sphere into the cylinder. And the sphere would displace water. Water would splash out of the sides. And then once he had put the sphere all the way down into the cylinder, he would lift it back out and he would measure the amount of water that remained. And every time he performed the experiment, the water level was about right to here. And he measured it very carefully, many, many times. And he found that the water remaining was 1/3 of the water that he started with. He reasoned, therefore, that the sphere had displaced 2/3 of the water. So the volume of the sphere was 2/3 the volume of the overall cylinder. You see, now let me go over that again. He would drop the sphere into the cylinder and it would displace water. And the water left over was 1/3 of the original amount of water in the cylinder. 1/3 the volume, you see, was left over. And he reasoned that the sphere had displaced, had taken the place of, its volume had occupied, you see, 2/3 of the volume. To throw it out, it had to occupy the volume inside the cylinder. So it threw out 2/3 of the volume of the cylinder. And so he made his calculation this way. He said the volume of the sphere then is 2/3 of the volume of the cylinder. And this is so wonderfully mathematical. In mathematics, you want something that has great impact, and yet its beauty is in its simplicity. And that's what this is all about. It's a very simple idea, as it turns out, but it took a long time for him to come up with this. So the volume of the sphere is 2/3 the volume of the cylinder. The volume of the cylinder is pi r squared h. We just talked about that. So now we want 2/3 of that. The trick here is the substitution for the h. Now come back over here and let me show you this. The height of the cylinder, you see here's the height of the cylinder. Well, what is that in terms of the sphere? Now, this point right here is the very middle, you see, of this circular top. and this point right here is the very middle of the circular bottom. And so the height then of the cylinder is exactly the height, I guess you'd say, for the sphere. But what is this distance in terms of the sphere? Well, it's a diameter. And a diameter is 2 times the radius. So this height of the cylinder is nothing but 2 times r. So we come back over here. The height of the cylinder is 2r. And now just multiply everything out and we get this. Here's how it goes. The 2 times this 2 gives this 4, and the 3 is this 3. The pi comes down. We have r squared right here. Another factor of r here. Oh, altogether we have 3 factors of r, so we use the exponent 3 on the r. So it's 4/3 pi r cubed for the formula for the volume of the sphere. Now, by the way, this illustration was the illustration that was on Archimedes' grave stone when he died in his honor. Let's go through the calculation. If we say that the sphere has a radius, let's say, of 2 inches. So that's 2 inches, and all we do is replace within the formula. There's only one variable here. You see it's r. Well, actually there's 2. There's the volume and the radius, but all we have to do is plug in for one item and we can figure the volume. So the volume then is 4/3 times pi times the radius cubed. Now this means we have 3 factors of 2. 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. So this really is 8. So this volume then is 4/3 times pi times 8. We would make this calculation first, and I want to emphasize that here. And then we multiply all this out to find the volume to be 33.49 cubic inches. Let's talk about finding the volume of some solids which are the composition of the regular solids that we've kind of looked at before. And we're going to find, just as we did earlier when we were talking about area problems, that sometimes we're going to have to add volumes in order to make the calculation, and sometimes we'll have to subtract. Let's take a look at an example of each one. Here we have a situation where the figure kind of looks like a mailbox, or if we change the dimensions a little bit from inches to meters or something like that, maybe it's a walkway with a canopy over it or something like that. You can imagine it in a lot of different situations, but let's suppose that we want the volume of this figure. Now, we kind of divide our thinking into 2 figures within the one figure. We kind of have to have a cylindrical affair right on top with this canopy thing, or the top of the mailbox, or however you'd like to think about it. But it's half of the cylinder. It's the kind of the upper half of a cylinder for up here. And then this part of it is just a regular old ordinary everyday household rectangular solid, you see. So for the volume of the whole thing, we can think of the volume of the rectangular solid plus half of the volume of this cylinder part. And we might put that into some kind of equation format. We might say that the volume of the solid is found by finding the volume of the rectangular solid plus half of the volume of the cylinder. You see, you might just do this, and then an equation will emerge from it, or a formula will emerge from this idea. The volume of a rectangular solid is length times width times height. And then over here, the volume of a cylinder is pi r squared h. But we want half of that, so it's 1/2 times this. You see, and now we go fetch the information that we need for all of the items that we have to replace for, all the letters. Now, the length, width, and height of the rectangular part. Now, you can think of this in a lot of different ways. You can think of area of the base times the height, and that would be just fine. But the point is, when you're multiplying length times width times height, or LWH, you are just multiplying the 3 different dimensions, and the order doesn't make really any difference. You can think of the base as being this 24 by 6, so length, width, height. That's the way I'm looking at it over here. Length is 24, the width is 6, and the height is 4. Now, let's look at the cylindrical part. If this is 6 inches, and then that is 6 inches. But this 6 inches, you see, is a diameter for this circular end of our cylinder. And the formula is requesting the radius. So we want half of the 6. We want the distance from here to the edge, and that would be 3 inches. And that's what we're looking for. So, let's stay right here just for a second. The cylindrical part, the cylinder part, it has this as its depth. You know, if it was standing up, the height would be kind of obvious. It would be how high it is. But it's not. It's not standing up. It kind of goes this way. But we have to treat this distance as the height, you see, for our cylinder, because the base of the cylinder is out here and it kind of stretches in that direction. So think about those kinds of things when you're putting together the formulas. So 24 then would be the height of the cylinder. So over here, filling in, pi is 3.14, r, the radius is 3, and the height of the cylinder is 24. And now it's just a calculator punch from here. So 24 times 6 times 4 turns out to be 576. And this product turns out to be 339.12. Don't forget that the 3 has to be squared before multiplying times these other items over here. All right, then adding these two together, we find the total volume of the figure to be 915.12 cubic inches. Here's another figure, and this figure is drawn in your textbook, and I recommend that you look at it in your textbook because I'm not such the greatest artist here for this kind of thing. But it's just kind of like having a block with a cylinder cut out of it, you see. So we're taking this cylinder, it's almost like we're drilling a hole in the cylinder. Excuse me. We're drilling a cylindrical hole in a block, you see, a three-dimensional block. And the block is 30 by 40 by 80. And the cylinder that we're drilling out has a diameter of 28 meters. Now, if we're talking meters here, this is a very big object, you see. So it wouldn't be like a little block of wood or anything like that. This would be an enormous kind of thing. I can't imagine what this might be used for. It might be useful in some kind of reactor program or something like that. But let's make the calculation. We're trying to calculate the amount of material that is left when this cylindrical part is drawn out, or when this is manufactured, how much material is used in the manufacture of the item that we see here. So the cylindrical piece is not in there. It's just this outer piece that we're really finding the volume of. So the technique for finding the volume of the solid is to find the volume of the rectangular solid altogether and then take out or subtract the volume of the cylinder. So that's the idea, and we write that down. The volume of the solid is the volume of the rectangular solid minus the volume of the cylinder. And the volume of the rectangular solid is LWH, and the volume of the cylinder is pi r squared h. And then we go and get this information from the nature of the problem. So we come back over here, and for the rectangular solid, the 3 dimensions are 30, 40, and 80, and just pop them in to LW and H. It doesn't make any difference the order. We can think of any of these dimensions as the length, any as the width, and any as the height, just as long as they're all different from one another. Now I'm using, once again, the area of the base times the height idea. I believe I did. Yeah, I did. The 80 as the length, 40 as the width, and 30 as the height of the rectangular solid. All right, then for the cylinder, it is, remember, the radius that we need, and we have a diameter here. This is 28 meters up and down, and we want half of that, or 14. So 14 is very important, and the height of the cylinder would be this distance, and it would be the 80. So filling in over here, I have the 80, 40, 30, but more important, I think, is the radius here is 14, and the height of the cylinder is 80. All right, then going through the calculations, we find these numbers for the volumes of the rectangular solid and for the cylinder. Subtracting here, we find that the figure then has a volume of 46,764.8 cubic meters. Pretty big object.